In this video, I'm going to talk about something called the fundamental theorem of algebra. And basically what this theorem is going to tell us is it kind of counts the number of answers we can expect to have to a polynomial equation. So if the degree of the polynomial is n, we will have exactly n solutions. And that is including something called a multiple zero and an imaginary solution. Multiple zero means you could have the same thing twice. You would count them separately. And imaginary solutions obviously are the ones with i's in them. So just to give you guys an idea of why this theorem even works, I took an equation with x to the third power in it, and I factored it. We don't know how to factor it yet, but just trust me, it factors into this. And if you were to solve this for x, there's going to be x equals 1, x equals 6, and x equals -2 for our three solutions here. It was a degree 3 polynomial, so we had 1, 2, 3 solutions. So that kind of makes sense if you think about it. On our second problem over here, if we actually solve them, we have x equals 4, x equals -7, x equals -7, and x equals -10. If you were to FOIL these out, you would get something with x to the fourth power. So we have 4 distinct solutions. The thing is the -7 repeated twice. So like there's 3 different solutions for -7 and -10. But for this theorem to work, we count these separately. So we would still say these are 4 solutions. What we would say though is that the solution -7 has a multiplicity, of 2. So multiplicity just means if you have it repeat, it's how many times it repeated. So if you count the repeats separately, there are 4 answers for an x to the fourth problem there. So to close out this video, I just have one other kind of example here. We're going to create a polynomial in standard form, and I'm going to give you the answers that I want to have. It's going to be 4i, -4i, and 5. But our solution of 5 is going to have a multiplicity of 2, which means essentially there's 2 5s. So if one of our solutions is going to be 4i, think back to when we put it in factored form, we have to have an x minus 4i. If we want a -4i, it's going to be x plus 4i. If we want 5, it's be x minus 5. And we're actually going to have 2 of those x minus 5s because it has a multiplicity of 2. This has to equal 0 so that the solutions actually work like they're supposed to. But this isn't standard form. So we would just multiply these out and kind of get our new equation. It's easier if you take the I ones and multiply them together. If you do FOIL on these, you get x squared plus 4ix minus 4ix minus 16i squared. Ix's cancel, so you get x squared. And if you remember, I squared equals -1, this turns into plus 16. So my first 2 guys, I multiplied and I got that. I'm actually going to just go ahead and multiply these guys together. I'm going to get x squared if you do the FOIL. X squared minus 10x plus 25. And then you just proceed to multiply these out. It's kind of tedious, but not terribly crazy. So let's see if I can do this fast. We have x to the fourth, 10x to the third. I'm just going to write them all out. Minus 10x to the third plus 25x squared plus 16x squared minus 160x. So obviously not a terribly pleasant answer here, but if you just do your FOIL, you'll get your eventual equation. So we're looking at x to the fourth minus 10x to the third plus a 41x squared minus 160x plus 400 equals 0. That is our standard form equation that would have the solutions they asked for.